Last time we talked about a variety of issues associated with social inquiry. What I want to do today is take a more specific focus. This time, in this meeting, we'll look at measures of central tendency, and for the most part, those measures are known to you. A mean, a mode, and a median. You know a mean probably under the label of average, but a mean, a mode, and a median are measures of central tendency. Next time we will look at measures of variability, and some of those measures may be less familiar to you. But this week, this meeting, I want to talk about measures of central tendency. Measures of central tendency. In fact, measures of variability as well, but measures of central tendency are a means of communicating something about a group of scores with a single score. The most common of these single scores, these measures of central tendency, is the average or mean. I could collect the GPA of everybody in the class and compute the average of those GPA scores, and I would have a measure of central tendency, the mean score, which I would use to describe the class in general, the group of scores in general. You understand that no matter how good that measure of central tendency is, and by good I mean how well it describes the group, it does not contain all of the information. That is, in order to be informed about all of the information, each of you would have to examine all of the individual scores. Because let us presume that the average GPA in here is 2.726. Not each of you has a GPA of 2.726. That is, there's some information, some of you are not described very well by the measure of central tendency. There is information that has been lost. So, in determining which measure of central tendency to use, the question you have to ask is, how well does this measure retain the original information? Typically, the answer is the mean, for reasons we will see. But sometimes that is not the case, for reasons we will see. But given that there are multiple measures of central tendency, the mean, the mode, and the median, choosing which of these to use is a function of a single criterion, and that is which of these measures does the best job of retaining the original information. Let's deal first with the mean. Let us presume that we have a set of scores between 0 and 10 that describe person's scores or person's score on some test. Person 1 scored a 5, person 2 scored an 8, person 3 a 7, person 4 an 8, person 5 a 4, person 6 a 2, person 7 a 9, person 8 a 10, person 9 an 8, and person 10 a 3. So the n here, that is the group or sample size, you would agree is equal to 10. That is, there are 10 scores that range from a low of 2 to a high of 10. I presume these scores are the X's. And I talked last time about X and Y, and we used X and Y last time to distinguish between independent and dependent variables. I'm sorry to tell you, but X in this context doesn't mean either. It has nothing to do with dependent and independent variables. Lowercase x is simply the way of representing a score, so that 5 is x lowercase x1, x1, and 8 is lowercase x2 down to 3, which is x10. Collectively, they are xi's. They are the individual x's, the individual scores. And I presume that each of you knows how to compute the average or mean of these scores. In order to compute the mean of the scores, or the average, we have the sum of, from 1 to 10, the xi's divided by n. This is the process that you go through when you compute an average, I'm sure. Sigma simply means sum together. Add together all of the individual x's, all of the individual scores, and then divide by n the number of scores. So we would add together the stream of scores, 5 plus 8 plus 7 plus 8 and so on. So we have 13, 20, 28, 32, 34, 43, 53, 61, 64. Would everybody agree that the sum of xi is 64? That is, if you add all of the individual scores together, you arrive at a score of 64. I'm sure that automatically you know then that when computing an average or mean, you then divide by the number of scores. The number of scores in this case is 10. So that the mean of these scores is 6.4. The average score on this test was 6.4. Are there any questions about how to compute a mean or what the average or mean means? I think this is meaningful to everybody. I want to add one additional piece of information. At the very outset of the last lecture, I indicated that it's important to distinguish between populations and samples. That although researchers seek to make statements about populations, they do so by observing samples and then making inferences about the population. So we should distinguish between population means and sample means. And we simply use Greek letters to do that. If mu indicates a population mean, uppercase X with a bar over it, X bar, indicates a sample mean. So if this was a population of scores, all of the scores in which we had an interest, mu would equal 6.4. The population mean would be 6.4. If this was simply a sample in which we had an interest, X bar would equal 6.4. It does not matter how clearly whether you are seeking to talk about a population or whether you're seeking to talk about a sample, the computational process is absolutely the same. You sum together all of the individual scores and then you divide by the number of scores. This is easy, right? Man, and I thought this was going to be difficult. Let's get rid of the notion of different. Simply remember that the mean of the scores was 6.4. There are other things that we can do with this group of scores. We can arrange them into a frequency distribution, would you agree? That is, we can list the xi's and the frequency with which those individual scores occur. And the scores available are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 0 appears 0 times in this set of scores. 1 appears 0 times in this set of scores. 2, 3, 4, and 5 each appear once in this set of scores. There are no 6s in the set of scores. There is 1 7, there are 3 8s, there is 1 9, and 1 10. Would you agree? So that we now have, again, 10 scores. 1, 2, 5, 6, 7, 8, 9, 10. Yes? No? A nod, a shake of the head, a little reminder to me that there's intelligent life out there. A frequency distribution. Let's now then think in terms of a second measure of central tendency, the mode. The mode is simply that score that occurs most frequently. Well, let me rephrase that. It's that score or those scores that occur most frequently. In this distribution, one score occurs more frequently than any other score, would you agree? And that score is 8. It occurs 3 times and no other score occurs more than once. So, first of all, this distribution has a single mode, and that mode is 8. Would you agree? Would you agree as well that there can only be one average or mean to a set of scores? You can't have the same set of scores and compute 3 means for it. You can, however, have distributions that are, this distribution is unimodal. It has one mode. You can clearly have distributions that are bimodal or trimodal and so on. That is, let us suppose in this distribution that rather than one person scoring 3, 3 people had scored 3. Would you agree that under those circumstances the distribution would be, the set of scores would be bimodal? That is, it would have 2 modes. One mode would be 3 and the other mode would be 8. Yes? So whereas you can have only one mean to describe a set of scores, you can have multiple modes. Let's look now at the third and last measure of central tendency, the median. The median is the 50th percentile. The median is that score which divides the distribution in half, such that half of the scores are above the median and half of the scores are below the median. It's just like the median in the road. The median in the road divides the road itself in half. Traffic on one side goes one way and traffic on the other side hopefully goes the other way. When describing data sets, the median is that score which divides the distribution in half such that half of the scores are higher than the median and half the scores are lower than the median. In this instance then, we are seeking a score above which are 5 scores and below which are 5 scores. Yes? And the median is that score in the middle. Would you agree? Well, let's count through the scores from the lowest to the highest. 1, 2, 3, 4, 5. So 5 scores are 7 or below, and 5 scores are 8 or above. So that the median in this instance is 7 plus 8 divided by 2. It's 7.5. That is, it's the score that is equidistant from the 2 adjacent scores. So the median in this instance is 7.5. Let me ask at this stage, are there any questions about the mean, the mode, or the median? Either on the one hand, how you compute the mean or mode or median, or on the other, what they mean, what they are. So if on the exam you were required to compute the mean, the mode, and the median, you could do that. Nolo problemo.
Let's say there's an odd number instead of like 10. What would you do for median, let's say?
If there is an odd number of scores, ideally, if there were 11 scores, the median would be the 6th highest score, or the 6th lowest score. That is, there would be 5 scores below it and 5 scores above it. It would be a real score in the distribution. 7.5 is not a real score in the distribution because nobody achieved that score. But if you have an odd number of scores, then the median is a real score in the set. And in this instance, if you had 11 scores, it would be the 6th highest score because then 5 scores are lower and 5 scores are higher. An even more complex situation occurs when, let us assume, we were seeking the 5th highest score and we got as far as 8. There are 3 scores there. 8 would be the median under those circumstances, but you wouldn't have precisely the same number of scores above and below 8. Sometimes when when you seek to compute the median, if you're looking for the 5th score or the 19th score or the 104th score, they're all the same. When you count from the lowest to the highest, the 128th score, the one you're looking for, and the 129th score, and the 130th score, and the 131st score are all the same score. That score is the median, but what it does, the implication of that, is that you do not achieve this precise splitting of the distribution in half. There will be slightly more scores above it than there are below it, or there will be slightly more scores below the median than above the median. On an exam, you're not going to confront that situation. And in its most straightforward sense, in its purest sense, a median score is the 50th percentile. It is that single score that divides the distribution in such a way that half of the scores are higher than the median and half of the scores are lower than the median. Are there any other questions about any of these measures of central tendency? The argument is made sometimes that statistics can make you believe anything. Part of the reason for that is apparent in these scores. Let's remember what we're doing first of all. We're seeking to describe a set of scores by computing a single score. It's a more efficient way of dealing with data. It doesn't make any sense for Nielsen to collect data on any number of homes in the United States in terms of television viewing habits and television viewing time and just dump that data on your front door and say, you make sense of it because I can't. One of the first things that the Nielsen folks do is compute an average viewing time score. And the average family television viewing time in America is approximately 7 hours. 7 hours of television a day. 2 observations. One that's not really, 3 observations. It's like the Spanish Inquisition. Nobody expects the Spanish Inquisition. It's their ruthlessness and their speed. Well, actually, it's 3 things. It's their ruthlessness, their speed, and their secrecy. It's a Monty Python thing. 3 observations, if I can remember them. 1, that's a lot of TV viewing. 2, it's an attempt by Nielsen to describe, obviously, a large number of people with a large number of different television viewing scores with a single score. And that single score is meaningful to you and me in some intuitive way up here. We take that score of a little over 7 hours to be somehow informative about the group as a whole. My third observation is that I suspect that very few, if any of you, watch TV 7 hours a day. So that this measure of central tendency that Nielsen is using is not very informative about your television viewing habits. That does not necessarily mean that in this instance the mean is a bad measure of central tendency. It may simply mean that, first of all, there is a high level of disagreement, dissimilarity, a high level of what we'll come to call variance in the individual scores. Some people watch a lot of TV. For some people, they got it on 25 hours a day. They actually turn it on before they turn it off before they turn it on. They turn it on before they turn it off. One of the two. They get up before they go to bed. You know, some people watch an average amount of TV, 7 hours a day. And some people watch very little television. That is a high level of dissimilarity or variance in the set of scores. A second observation is it may simply mean that rather than compute one measure of central tendency, you compute multiple measures of central tendency. That is, you break down the group as a function of some attribute, potentially age, because as one ages, generally one watches TV. People who are elderly tend to watch significantly more television than people who are young. So we could define what it means operationally to be young or middle-aged or elderly, and then we could compute an average viewing time score for each of those three groups. And we would probably generate three scores that were more reflective of the groups that they were designed to be representative of than this single indicator that Nielsen generates of a little over 7 hours a day. The fundamental issue here is that we're trying to describe a group of scores by calculating one score. A second observation is that you have three choices. You can compute a mean, you can compute a mode, or you can compute a median. And each of those is a valid measure of central tendency. It's not like I made one of these up before I came in here, or made two of them up and there's really only one real one. They're all available on the shelf when you go to compute a measure of central tendency. So the issue then is, which of these do you choose? I said at the outset that you make your choice based upon the score, that is the measure of central tendency, that retains the maximum amount of original information. On that basis, which of these measures of central tendency would you select to use? Would you select the mean, the mode, or the median to describe this set of scores? You would select the mean. You'd select the median. Why would you select the median? You might want to push down and tell us all, and tell future generations.
Well, I assume, being that it's the 50% mark, that's where you have the most, I'll not explain myself, the most accurate information.
Okay.
Comparatively to the other two options.
Doesn't matter how clearly you explain yourself. You got a rationale for selecting the median. That's fine.
In my opinion, I'd select the mean, because when you're doing the median, if you get like a 7.5, that's not reflective of the like you said, 7.5 is not like a real median.
You would select the mean because the median is not necessarily a real score.
Yeah.
Well, neither is the mean, because none of these scores is 6.4. I will tell you, you made the right, you chose wisely. You chose unwisely. And you know what happens in the movie? You now die. Your skin goes away and bones, and you explode. and you go on to some serene life. But it's the mean is the best indicator, or we might select the mean as the best indicator, not because the median isn't a real score in this instance. It's because the mean, unlike the other two measures, is sensitive to all of the scores in the set. If you look at your notes, what does the formula for the computation of a mean say to you? It says the first thing you do is you add together all of the scores. Yes? The numerator in the computation of a mean is the sum of xi. That is the sum of all of the individual scores. So the first thing that formula tells you to do is add together all of the scores. Therefore, by definition, the mean is sensitive to all of the scores in the set. Whether there are 2 scores in the set, 102 scores in the set, or 14,002 scores in the set, you add them all together. Clearly that's not the case with the mode. The mode is just that score or those scores that occur most frequently. So when computing a mode, you are sensitive only to those scores that occurred most frequently. You're not sensitive to any of the other scores. All you're doing when you compute a mode is you're running your thumb down the frequency column of the frequency distribution, trying to identify that score or those scores that occurred most often. You're not looking at all of the scores. Likewise, when you compute a median, you're looking for a single score. You're looking for the middle score. You're looking for the 50th percentile. All you're doing is counting your way up or down the frequency distribution, again, the frequency column of the frequency distribution. You're insensitive to essentially every score in the set because you're seeking out only one. Under normal conditions, the mean is the preferred measure of central tendency. And it is the preferred measure of central tendency because it does a better job of retaining the original information than do the alternatives. And it retains, the key to the retention of original information in this instance is that you have to add together all of the scores. That is, the mean, unlike the mode and unlike the median, is sensitive to all of the scores in the set. Are there any questions? Are there any comments? Anybody like to leave the class? Anybody like disappointed with what they got? I wanted it to be more complicated than that. If there's something magical about the mean, why do some researchers, some government agencies, not use the mean? They select another score, another measure of central tendency. For example, every year the government releases data regarding the family income in America. But they don't release information, they typically don't compute information or use information on the average family income. That is, they don't compute the mean income of all the families in America or all the families in their sample. Instead, they talk about the median family income. Why would they do that? Besides the fact, yes.
The top 2% of this country controls the majority of the wealth.
That sounds like a political statement to me.
It's a true statement.
I'm just joking. I'm just joking, yeah. You'll change us all into socialists. 80% of the wealth in the country is controlled by the top 2%, or something extraordinary.
Not that much.
The problem with income data is precisely what you've indicated. The problem with income data is that if you were to plot the distribution, right, here is dollars, and here is the frequency with which people earn those, families earn those dollars, going from $0 up to some other number of dollars, some great number of dollars. The distribution of family income is sort of like this. That is, most of us earn less than however many dollars is here. And then a few people earn super dollars. Why is that a problem? Why is that a problem in terms of using the mean score to describe the set?
Because it's not a direct representation of the representation of the population.
It's not a direct representation of the population. Well, yeah, but we could say that about any mean score, that it's not necessarily a reflection of everybody in the group.
But when you use the median, then you're setting the bar. You're setting 50% of the population lives above here, and 50% of the population lives under here. So you're giving more precise cut up, or slice of the pie or whatever, of the whole money.
The problem here is actually, isn't it always the case? When you take these history classes and they say, what were the advantages that the Prussians had in the Franco-Prussian War? Well, the first advantage is they were fighting Francos, but that's just an English view, and I didn't mean it for posterity. I didn't mean it. I have nothing against the French. I think they're fine fighters and very chivalrous. And I think they have a military history to prove it. I'm just joking, because I'll offend somebody. I've offended a lot of people already. The issue here is that the advantages of something are often as well the disadvantages of something. One advantage of the Prussian army was its size, which means that one disadvantage of the Prussian army was its size, because anything that's big moves slowly. The advantage, the great strength of the mean is that it is sensitive to all of the scores in the distribution. Its weakness is that it's sensitive to all of the scores in the distribution. And when a mean is being used to describe a distribution of this sort, in which there are the frequency of these extreme high scores is very low, what these few extreme outliers serve to do is they pull the mean towards them. They exert an undue influence on the mean. You have a lot of family incomes around about $20,000, $30,000, $70,000, $200,000. And then you have a small number of family incomes of $28 million, $84 million, $176 million, $242 million. And I wish so much that I were in that group. Unfortunately, as a university faculty member, I only earn $4 million a year. With endorsements, that's $6 or $7 million. You know, I have my own set of lecture shoes, Nike, with Nike. The problem, the weakness with the mean in this sort of circumstance is that because it is sensitive to all of the scores in the set, it is necessarily sensitive to those extreme outliers and pulled towards them. It is not a problem. It is not a problem when you have extreme outliers at the other end of the distribution. That is, if you administered a test and a lot of people scored very high on the test and a lot of people scored very low on the test, that is not a problem for the mean, because there's some sort of counterbalance between the extreme high scores and the extreme low scores. You understand the problem here is that there is no negative analog to the $298 million. You can't earn negative $298 million. If you do, you're in a hole. So the problem here is not that there are outliers, not that there are extreme scores. The problem is that those extreme scores exist only at one end of the distribution. And so they pull the mean score towards them. So that what was its strength, that it is sensitive to all of the scores in the distribution, becomes in this context its weakness. That it's sensitive to all of the scores in the distribution. Are there any questions about anything? The mean, the mode, the median, the Franco-Prussian War, the military history of France, the likelihood of England winning the European Football Championship next year. Why did Manchester United lose to Arsenal on Sunday? What's the best Indian food in town? None of these. You have
Actually, I have a comment.
You have a comment. Yes.
If you go to Google and you type in French victories and you press feeling lucky on the top, it will come up results saying, did you mean French defeats?
I rest my case. Or should I say, I didn't know anything about that. I really didn't. Oh, we're going to get ourselves in trouble together. Because you see, at some time or another, the university is going to hire a French president. That French president will see these lectures, you and I. The rest of them are just dissonance. It wasn't me. It wasn't me, it was those two. I never thought that. So we're all straight with measures of central tendency. Let's just very briefly then start talking about measures of variability, which is the topic in chapter 4. Measures of variability. Measures of variability simply seek to express how similar or dissimilar the set of scores are to one another and to the measure of central tendency. Measures of variability seek to provide information, or should provide information, about how similar, dissimilar the scores are to one another, and how similar, dissimilar they are collectively to the measure of central tendency, usually the average or mean. The first measure of central tendency that we'll look at is the range. To compute the range, you simply do three things. You identify the highest score in the set. You identify the lowest score in the set. And then you subtract the lowest score from the highest score. So the formula for range is range equals the highest score minus the lowest score. What is the range of the 10 scores that we have in some disagreement? The highest score is 10. The lowest score is 3, 2. Hang on a second, I'll get to your question. The highest score is 10. The lowest score is 2. The range, then, of these scores is 8. You have a question?
So it's the highest score that's actually scored, or the highest possible score?
It's the highest actual score minus the lowest actual score. The theoretical range would be the highest possible score minus the lowest possible score. So the theoretical range with regard to our test scores is 10 minus 0, which is 10. But the observed range, typically referred to simply as the range, is the highest score 10 minus the lowest score 2, so that the range of this set of scores is 8. Having said that, as a measure of variability, the range is useless. And we shall remove it from our memories. Well, not necessarily, because we might see it on the first exam. Why is the range statistic absolutely useless as a measure of variability? Let's go back to essentially the first words I think that came out of my mouth today. you have all sorts of options when selecting a measure of central tendency, and you have all sorts of options when selecting a measure of variability. How do you determine what selection to make? The primary criterion is you select that statistic that retains most of the original information. That means operationally that is sensitive to all of the scores, or sensitive to more scores than any other indicator. How many scores is the range sensitive to? 2, the highest and the lowest. We could change everything in between. We could change everything in between. We could change all of the other scores to 4, and it would not alter the range. The range would still be the highest score 10 minus the lowest score 2, which would be 8. But if the other 8 scores were all 4s, clearly the set would look very, very different. The set would be very similar. Yes? No, you've got to give me more than let me put it another way. Once upon a time, there were 2 sets of scores. One set of scores were different. There was a 10, there was a 9, there were 3 8s, there was a 7, there was a 6, there were no 5s, there was, it's the set we had. And the lowest score in that set was a 2. There was also, living in a faraway land, another set of scores. The highest score in that set was also a 10, and the lowest score in that set was also a 2. But every other score in that set was a 4. Clearly, the second set is a set of numbers that displays a high degree of similarity, a high degree of homogeneity. 8 of the 10 scores are the same, but the range is still 8. When we look at the first set of scores, this is a relatively heterogeneous group of scores, but the range is still 8. The range tells you nothing then about the internal structure of the group of scores. And if it tells you nothing about the internal structure of the set of scores, it's useless, because that's what it's supposed to do. It's supposed to tell you about the internal structure of the set of scores. So the people of this land took the range and they put a hole in its head this big. This is Steve Martin. Now I think about it, they put a hole in it this big. No, now I think it was this. They got rid of the range. The range is uninformative. It provides no information about the internal structure of the data set. We will look next time at 2 other indicators that do provide that information. One is the standard deviation, and the other is the variance. The standard deviation of a sample is indicated by the letter S. The standard deviation of the population by the Greek letter sigma. Variance is S squared or sigma squared. That is, the standard deviation equals the square root of the variance. There are just two things here. One is we're again distinguishing between population scores and sample scores. The notation for sample standard deviation is S, and for sample variance, S squared. For population variance, sigma, and for population variance, sigma squared. The second thing I'm pointing out is that these aren't selected by chance. S and S squared, sigma and sigma squared. S is the square root of S squared. Sigma is the square root of sigma squared. That is, standard deviation is the square root of the variance. So while you can generate two numbers, one the standard deviation and one the variance, computationally, all you're adding to the computation of standard deviation all you're adding to the computation of standard deviation rather than variance is you're adding a step where you take the square root of the variance score. These are not two independent measures, as mean and mode were independent of one another. They didn't share, computationally they shared nothing in common. Computationally, standard deviation and variance share almost everything. Are there any questions? If you will take a look at chapter 4 that discusses variance and standard deviation. Some of you are familiar with variance and standard deviation, but some of you are not. And we'll spend a little time going through this because I think we're now moving into areas that are less familiar to some of you than the stuff that we've talked about so far. Ta-ta for now.